Hello and welcome. This is an introduction to experiment 5 and day 1 of the experiment. You might find watching some of this video and pausing might be helpful throughout your doing of day 1 of the experiment. We see some key conversion factors and some introductory statements that you can read. Very brief introduction is that all molecules have some optimal set of bond lengths, angles, and or dihedral angles. And these parameters give a molecule a lower energy than any other arrangement. This is called the global minimum. Now, some molecules don't even have angles or dihedral angles, like H2 just has a bond length. Water only has a bond angle and two bond lengths. A molecule like methane would only have the bond length of the CH bond, and then the bond angles are all 109.5 for a perfect tetrahedron shape. And then it doesn't even have any other minima. So some molecules don't even have this local minima problem that we talked about in the computational chemistry introduction. Molecules that are a little bit bigger, though, are going to have various possible local minima that we may want to consider their relative energies and find the lowest to identify the global minimum. And that all of this is through computational chemistry is collecting data that through experiments may be challenging or sometimes even impossible to easily determine. And so we can get a lot of data from a computational chemistry experiment that we can then try to find things that we can compare against in the literature so we can see which methods work or maybe don't work as well. So for day 1, activity 1, this is really all the activities for the first day. What we're looking at is a hydrogen molecule at the HF631G star method. A few things before we get started. Computational chemistry, of course, looks at one molecule isolated in the gas phase. This file or this set of experiments was written for using Spartan. We're probably going to mostly use WebMO. So use WebMO to build hydrogen and run that calculation. And you're doing an opt plus freq calculation for the optimization plus vibrational frequency analysis calculation. And then just report out the results for the bond length. I'll actually go through here how you can get some of this data here from your molecule. So you may actually run your calculation, hit pause, and then come back afterwards and try to figure out how to extract your data. Let me go to my job manager so you can kind of see the jobs, what they look like once they finish. So you can click on H2 once you run this calculation. Pretty easy molecule to build and to set up the calculation on. Watch the WebMO videos for how to set up your calculations and extract some of the data from them. I'll show you here as well. The molecule here, if you want to get some of the information, you may click the mouse cursor and you can click the two bonds and it shows you the bond length here, so 0.735 angstrom. Important to note that I ran a 321G calculation with HF, so I ran maybe a different basis set than you're probably using. Your RHF energy here, this is going to be the electronic energy. So the RHF energy, this is your electronic energy. So I call it the E0K, the energy at 0 Kelvin, because it's the energy the molecule would possess if it were to exist at 0 Kelvin. Vibrational frequency is all the way towards the bottom, so the vibrational mode here, this is our frequency in wave numbers. So you may want to note the units here. Electronic energy was in Hartrees, that's atomic units. So AU is Hartrees. So like this AU here, 1 AU equals 1 Hartree. 1 Hartree equals 2625.5 kJ per mole. Okay, so then our 0 point energy is up here, 0 point energy, ZPE, also given in Hartrees. And then our heat capacity here, CV, cals per mole Kelvin, and our entropy, also in calories per mole Kelvin. Now, of course, you can convert calories to joules, and you'll have to do some conversions here as we continue with the activity. But the first part of the activity is kind of trying to make sense of the 0 point energy as being 1/2 h nu. It's truly 1/2 times the sum over all h nu, over all the vibrational frequencies. But we have one vibrational frequency for a diatomic molecule, so it simplifies down to a pretty simple equation. So we want to verify that the energy, the 0 point energy reported by, in this case, WebMO, is correct for the vibrational frequency. So what we want to do is convert our vibrational frequency to to actually, because remember, your frequency is really not a frequency, right? Because like an inverted wavelength is what the frequency is. So use the speed of light to convert that to an inverse second frequency, and then use that along with the equation for you use that with Planck's constant, so 1/2 h nu you see here. So to actually get the nu here, you want the frequency in inverse seconds. So you want the frequency in inverse seconds, so you can multiply by Planck's constant in joules times seconds. So simply take your vibrational frequency in inverse centimeters, convert it to inverse seconds, and then plug that into the equation here. That gives you your 0 point energy in joules. Then use your conversion for joules, convert that to maybe kJs per mole, and then kJs per mole over to the atomic unit or Hartrees to compare the ZPE that was output up here. So this is just making sense that the 0 point energy that's determined from that's reported in the file is truly from the calculation of 1/2 h nu. So it's a tricky calculation to do, but it just involves some conversions and using some equations, just like, just some basic equations like the speed of light. Part 2 is then using the idea that the H0K would be the E0K plus the ZPE. So it would be our electronic energy plus the ZPE. Then that allows us to take the heat capacity times temperature to then add on to the enthalpy at 0K to give us the enthalpy at 298K. Only issue here is you got to take into consideration units. So you got to maybe convert calories to joules, maybe joules to atomic units, or perhaps take the atomic units to kJs per mole. Do some kind of conversion to square the H0K into the same unit as CV times T. And then likewise for solving for the Gibbs energy, the idea here is that what you should be able to do is show that the enthalpy here, that this number of Hartrees here, can be found by taking your 0 point energy plus the ZPE, and then adding the heat capacity term, and then the free energy term here would be the G, should match up by then taking the H at 298K and the minus S times 298K. So it's just doing the work to try to figure out where it is that the enthalpy and free energy terms are coming from. The internal energy, I actually made a mistake earlier. The RHF energy is actually not the electronic energy. The electronic energy is the internal energy here. No, I'm right. This is the electronic energy. I think the internal energy, I'm not entirely sure. I believe the internal energy is this H0K. Then we take the E0K plus the ZPE. That looks about right. So I think that that's what the internal energy is. If you wanted to do a check on number 2, it should match up with the internal energy. So RHF energy is your E0K. This should be your H298K, and then the free energy, your G298K. So you're just getting a sense of where those values are coming from. Luckily, we're not going to have to do this calculation every time we run a calculation. If we want to run a calculation and get the enthalpy at 298K, we'll just know to grab the enthalpy value here. And then the last, well, not the last part of the day, but the last part on H2 is comparing the energy of H2 in atomic units, the bond length, and the vibrational frequency from a series of different methods. And these shouldn't take too long to run, so you might set some of these up, and if they take a little bit to run, just update the results, in 15 or 20 minutes after you have a chance to complete and run. So this is just getting a sense of, do you get a better result as you go to a bigger basis set? And do you get a better result as you go to an improved method? You can get a quick comparison there. Moving ahead, number 6 will be best discussed in a separate video. So we'll talk about basis sets and what it takes to get through number 6 through a separate video. And then moving on to number 7 and 8 and 9, Hartree-Fock neglects electron correlation. So it doesn't correctly consider the electron repulsion. So what do you think that's going to do to a bond length? Let's think about how if you don't allow the two particles that should repel each other to formally repel each other, what that might do to the bond length. And you might be able to see some of those results as you compare your table in number 5 with the known results. Which method and basis sets are best? So take a look at your data, try to figure out, is it really one of the better methods with the bigger basis sets, or is it not that particular method? And the last thing we might do is look at CO2, methane, water. We're going to use B3 ellipse 6311 plus G star star. That's 63G DP in a slightly different nomenclature system. And what we're going to do is we're going to compare as well to N2. So N2, we're probably going to find it's either inactive in terms of its vibrational mode, whereas the other molecules are. And so what I want you to think a little bit about is how absorption of infrared light, perhaps heat radiating from the surface of Earth, is going to be best accomplished with the components in air that are well below 1% of air. So the CO2, water vapor, methane, these are not major components in the atmosphere, but they are among the only components of the atmosphere that are capable of absorbing infrared heat. And so that's our introduction for day 1 and experiment 1.